Hi guys, we were discussing about electric potential energy. So, electrostatic potential energy, this we can understand by taking a test charge small q. Suppose I am having a test charge which is positive small q. So, the electrostatic potential energy of this test charge in an electric field. To know the electrostatic potential energy, I need to bring this test charge from infinity, all the way from infinity to at a location. Let me consider this as point B in an electric field. So this location is at a distance r. So this location is at a distance capital R from the center. Now I can define electrostatic potential energy at a point B, which equal to work done by me to bring this test charge from infinity to at that location. So if I can calculate the work done by me to bring this test charge from infinity to all the way to a location at a point B in this electric field. So my work done will be stored in this charge at here in the form of electrostatic potential energy. So that is the main concept. The work done by me will store in the form of electrostatic potential energy. Now if I write the expression for that, electrostatic potential energy at point B is equal to K. Capital Q is the source charge and small q upon the distance is capital R. So this we define as electrostatic potential energy. Whatever work I did, so that work will be stored in the form of potential energy. Suppose I want to displace this charge from point B to one more location, which is point A. So here if I take another location point A, I want to displace this charge from point B to point A. So if you take the point A is at a distance of small r another, so because it is having another location, so if I consider this as small r, now I can write electrostatic potential energy at point A, which equal to same K capital Q and small q upon by in this case R. Here I would like to write the potential energy difference. So to move the charge from point B to point A, I did work. So the work done by me to move charge from B to A. So to do the work, I spend my energy. So how much I spend my energy? So that energy will store in the form of potential energy difference. It means if you can subtract these two, so K capital Q small q upon by R minus K capital Q small q upon by small r. If you can subtract energy minus energy, you will get energy itself only. So this we define as potential energy difference, or this potential energy difference is nothing but the work done to move a charge from B to A within the electric field. So finally we can define the electrostatic potential energy of a charge. So the potential energy of a charge small q. So here the small q is a test charge. The potential energy of a test charge at a point, where the point is located, the point is present in the field of any charge configuration. It means the charge is present in an external electric field. So the potential energy of a charge at a point is the work done by the external force. Here I myself is the external force, the work done by me in bringing the charge q from infinity to that point. Now by using this electrostatic potential energy, so this is the expression for electrostatic potential energy, we will define electrostatic potential. So electrostatic potential, according to definition, it is defined as the work done per unit charge. Suppose if I can take the definition at here, the electric potential U is defined as the electric potential energy per unit charge. So V equal to U by Q. So we just defined that what is electric potential energy. So if this is electric potential energy at a location in the electric field, it is a K capital Q small q upon by R. To define electrostatic potential, so the electrostatic potential we define as, we can represent that with the capital V. So electrostatic potential capital V equal to work done per charge. So here work done will be stored in the form of the potential energy. So potential energy per charge. So here the potential energy, if we can write the potential energy of a charge at a location, it is a K capital Q small q upon by R over small q. Now here you can see we are removing the test charge magnitude. So the electrostatic potential or electric potential, in a simple word you can take the electric potential at a point in an electric field. It is defined as K capital Q upon R. Now so this is the electric potential value in an electric field. So if you can notice this expression, so this expression do not contains about the test charge. So this expression tells about the electric field itself, because it's only having the test source charge and Coulomb's constant and the location. Now by knowing this, we are going to express one more characteristic property of this electric field. Till now we expressed about electric force and after that electric field, and just before we expressed about the electric potential energy, and now we are expressing about electric potential. So if you can write its units, so potential energy units are nothing but joules, and you are dividing joules upon charge coulomb, so it becomes as a joules per coulomb. So joules per coulomb we termed as volt. So the unit of electrostatic potential is nothing but volts. So we define the electrostatic potentials. It is that the work done per unit charge, or for precisely if we can write the potential difference and the electrostatic potential energy relation. So the potential difference and electrostatic potential energy. So the relationship between potential difference and the electrostatic potential energy we can express as, so delta V equal to delta U upon by Q. So don't worry about that. What is this delta? Delta means nothing but the change. So if we are having the 2 points, so we can express the potential difference. So to explain this potential difference, I will explain with the help of one small example. So I hope you understood about what is electric potential. So the electric potential we define as the electrostatic potential energy per unit charge, or you can simply remember the work done, because the work stores in the form of the potential energy, the work done per unit charge. Let's try to find electric potential due to a point charge. So here I am considering a charge plus Q at origin, and I wish I would like to find electric potential at point P at a location within the electric field at a distance capital R, from the origin. So if I mention this is the distance capital R, I would like to find potential at point P. So that is my task. So to find that, I need to calculate my work. So let me take a test charge within the electric field. I am taking a help of test charge. So my test charge here, it is small q, or you can take q naught. So which is at a distance of x from the origin. So this test charge within the electric field, so that is at a distance of, you can take r, small r, which is at a distance small r from the origin. Let's consider this point A. Now I need to do work. Here you can see Q naught is also positive test charge and capital Q is also source charge. It means both of them, there is a Coulomb repulsive force will be there. Now I need to do work against that. Now work done by me equal to force applied by me to a small displacement, I can take dr. So then I can do the work, small work dw. To calculate my total work, so work done by me, I need to do integration. So small dw work done by me, which equal to the integral of force applied by me times dr. Now here we can see I need to bring from point A to P. It means I need to move along in this direction. Now my force direction and my displacement direction, they both are in the same direction, so there won't be any problem. But I don't know how much exact force I am applying. So to figure it out my force, I would like to take the help of the source charge. That is, the force applied by the electric field is exactly equal to the force applied by me, but this will be a negative. So because I am applying against the electric field and the electric force is applying against me. So in the place of the force applied by me, now I can replace the work done by me, which equal to integral minus electric force times dr. Now this minus tells about the force direction. Now we know the what is the electric force between them. If we can put the limits, so the limits is from A to P at here. So all the way I can put the limits from the A to P. So the work done by me which equal to, so I can write the Coulomb force formula here, negative of A to P, the Coulomb force which I can write K capital Q small q naught upon r squared times dr. Now we can flip this limits to remove the negative sign. So to remove the negative sign, the work done by me which equal to integral p to a, so k capital Q small q naught upon by r square times dr. Now if we can try to do the integration there, so the work done by me which equal to k capital Q small q naught integral p to a 1 over r square times dr. For a moment, suppose if I take a point where the force is 0. So for instance, let imagining this my point A is far away. I would like to bring the charge from infinity. So that is not within the electric field. So is at infinity. So because if you can take the infinity, so that gives us the elimination of the one of the limit. So the work done by me which equal to k capital Q and small q naught upon, now here my point A will become infinity and the point P is at a distance small r from the origin. So it's a 1 over r square times dr. So I can write it here from the O to infinity. The distance is infinity. From the O to P, the distance is R. Now it's easy to do integration. So if you can do the integration at there, so the work done by me equal to k capital Q small q naught. So 1 over r square integration I can get minus 1 over r times integral infinity to r. Now the work done by me, if you can substitute the limits, so k capital Q small q upon minus 1 over by infinity, minus into minus plus 1 over by r. So finally I can get the expression, the work done by me which equal to k capital Q small q naught 1 over infinity, the value goes to 0 plus 1 by r. The final expression we can write as the work done by me equal to k capital Q small q naught by r. So this is the work done by me to bring a charge from infinity to a location, which is point P within the electric field. So whatever work I did, so that work will be stored in this test charge, in the form of potential energy. So right now here I want to define electric potential at a point within the electric field. We can define electric potential as work done per unit test charge. Work done per unit test charge is known as electric potential. So if you can write electric potential as V, So I have the work done by me per test charge. Here I have taken the test charge as Q naught. So I can get the expression which equal to K capital Q small q naught upon by R upon Q naught. And the Q naught gets cancelled. So the final expression equal to K capital Q by R is known as potential at point P or potential at a distance small r from the origin. So if I write the expression for potential at point P, so at this point which is at a distance capital R, sorry, everywhere I need to change that as capital R. So since I consider this as capital R, so make a small change that, so that will becomes capital R. So over the entire integral, replace the small r with capital R. Let me do the correction. So here capital R is nothing but it is the distance. It is the distance from the origin to the point where I chosen. So finally the expression contains the term capital R. Capital R is the distance. Now we can write the potential expression, potential V equal to KQ upon capital R. So the potential at a point in the given location, so the potential at here, the potential at here at a point P, we can write that as potential at point P equal to K capital Q upon R. R is the distance. Now you select R anywhere in this electric field region from the origin to infinity. Now because of this electric field, we got another character which is scalar. So that is nothing but electric potential. So electric potential is a characteristic property due to because of the source charge. So if we can make much more simpler, so till now what we define, so in the electrostatics, let us see everything together. So first in the chapter electric fields, we started with electric force. For electric force, I needed two charges. One is the source charge, one is the test charge. So to define electric force, what we written? It is the Coulomb force K capital Q small q upon by R square. So electric force within the electric field. And after that, so we define electric field. So observe it carefully. So when we write electric field we define as force per test charge. So from the above expressions, so we can remove Q naught because Q naught will be gets cancels. Now, so these are the two characters we define in the electric fields, but the problem is that these two are vectors, so they are having directions. So to avoid that much complications, we started to talk about electric potential energy. So electric potential energy due to this positive charge. So to write the electric potential energy, it's the potential energy. So to that also we need to two charges. One is the source charge, one is the test charge. We can write electric potential energy because of this configuration. We can express as that is nothing but K, capital Q, small q upon by R. So this is the electric potential energy. Now I define electric potential. Electric potential we define as electric potential energy or work done per test charge. So in this above expression, if you can cut that, so K capital Q small q naught by R upon q naught. So q naught gets cancelled. We can write electric potential as K Q capital Q upon R. So try to just compare these four formulas. What is the electrostatic force? So electrostatic force between two charges, but electric field it is due to source charge, and electrostatic potential energy, so it is the potential energy within the location at a distance r. So this electrostatic potential energy is the stores in the test charge, and if you can remove the test charge, we are the getting a final easiest term, so that is nothing but electric potential. So we are defining electric potential as work done per test charge. So these all four characters are exist in this electric field. They all exist in this electric field. If you can take the electric field due to because of these configurations, so these all four characters are the existing. So all four characters are existing. To get the force, we need the two. One is the source charge and one is the test charge. But to get the electric field, we need to only the source charge. But to get the electrostatic potential energy, again we need the two charges. One is the source charge and one is the test charge. Finally, to get the electric potential is we need only a source charge. So how a source charge dependent character electric field and source charge dependent character electric potential, and source charge and test charge dependent character electrostatic force and electric potential energy. So if you can get clear between these four characters, so the things will become easier. So try to analyze them carefully.